Hello, everybody. My name is Philippe Antoine, and I'm going to talk to you about keeping on fuzzing and fixing Suricata. First, a few words about myself. So I have been part of the Suricata development team for more than 2 years now. And I love open source, network traffic analysis, cybersecurity, and actually fuzzing. So I guess that's why I'm doing this presentation today. This presentation may sound a bit familiar because at last SuriCon and last FuzzCon, Circo did a presentation about fuzzing Suricata. So that will be kind of a follow-up to it. So you can find me in this picture of the OISF team. So as an introduction, I will talk a bit about the threat model against Suricata. Then we will see an overview of the fuzzing results over the last year. And last, we will see the improvements which were brought to the fuzzing framework in order to get these results. So now for the threat model, and maybe start by a little introduction to fuzzing, because all of you may not be familiar with it. So what do I call fuzzing? It's a simple process as long as we have computer power available. We get some input and we process it and we check for bugs while processing it. So there is a lot of software hidden behind these things, but the main thing is to know that we process lots of inputs and maybe one input will trigger a bug. Maybe to make it a bit more clear, I will do a short demo about it. So as a demo, I'm going to run a first target, which is about HTTP2. So this is the command to start it, and it will produce lots of log lines after finishing initialization. So not follow everything, but let me just pause a bit. So we can see that in these first few seconds, we've already done 41,000 and something processing of inputs. And one thing which is interesting is that we kept 239 of these inputs because they induce different behavior so far. So, and the last one was reaching this function which was not reached before. And so the fuzzing keeps going on. And we are now at 500,000 inputs processed so far in this demo. So now let's take a look at Suricata and its inputs and outputs, because we said that fuzzing will process inputs. There is, I would say, 3 big inputs to Suricata. There is the configuration, which is all over the place, but is mostly a YAML file. There is the custom rules language, which does not have a grammar yet, which is below on the left corner. And there is the network traffic, which is the likeliest hit controlled by an attacker. So as a developer, we do not want any bug in Suricata, whatever the configuration, whatever the rules, whatever the traffic. Maybe as an end user of Suricata, you will just care about your own configuration and rule sets, and have only the network packets being the untrusted input. Or maybe you want to use rules from untrusted sources, and so rules are also part of the inputs. So why are we fuzzing Suricata? Because we want it to be a robust, reliable, resilient software. So we want to find bugs and fix them. And as a matter of fact, fuzzing is an efficient technique to do it. It's not the only one. There are other static analysis tools and compiler warnings and such. One of the advantages of fuzzing is that it gives us a reproducer case. So we have a low false positive rate because we can use this reproducer and easily debug after that. And in the end, we want to fix the bugs in Suricata so that Suricata as a cybersecurity software provides a positive cybersecurity value. And that is not obvious. It could have a negative value if we allow remote code execution because of a bug. So instead of protecting the network, will be the entry point for the attackers. I would say also that it could have a zero value if there is a complete denial of service. So if Suricata crashes because of null dereference or because of a rust panic, and there may be also a positive but reduced value if there is a bug which will result in a partial denial of service, such as a memory leak, a timeout due to quadratic complexity, or some logic bugs, evasions, and such. I am not sure what is worth between a complete or a partial denial of service, because complete denial of service, you will get aware of it. A partial denial of service is more stealthy, so maybe it's more dangerous, in fact. And so fuzzing help to assess the bugs by giving us the bug class. We can also easily see which versions of Suricata are affected, basically running a git bisect. But there is some more work to be done manually to see, especially if the bug is reachable in default configuration, or if we need specific options, specific rules. And in case the bug is triggered by network traffic, does the attacker need to control one or both of the network endpoints in a flow to trigger the bug? After this introduction, I would like to give you an overview of the bugs found by fuzzer since Suricata 6.0, so in about 1 year. Let me first explain my methodology. So the sources to create these slides are public. There is the OSS-Fuzz bug tracker, which is at bugs.chromium.org. And there is our Suricata bug tracker, which is on Redmine. So this is not exhaustive. We can see that we will take into account only bugs that reach the Git master branch. So for instance, we will not have the bugs which were caught before in the CI phase with the CI fuzz, for instance, which got 2 or 3 bugs, if I remember correctly. Then I did a manual review, which is, I guess, prone to some errors, to remove duplicates and to remove false positives. False positives being bugs in the fuzz targets instead of data itself. And you can download the complete data at catenacyber.fr if you want. So the overall result is that Fuzzing found 49 unique bugs in 1 year. 41 of them were only reported by OSS-Fuzz, and so the 8 other ones were also reported by other means. So the value of OSS-Fuzz is more in the 41 which were not reported by other means, I guess. Every bug which was found got fixed in the next version, except 4 bugs which got fixed before getting into any release. So this is a good thing. And there are 3 bugs which are not such a good thing. So 1 bug which was found in 6.0.0, which was only fixed in last 6.0.4, which was not a big impact bug. 1 bug which was also found in 6.0.0, but the bug was not found in SuriCata itself, but in PCRE1. And so the fix was to switch to PCRE2, which was a big change. So it was left until the next major version. And 1 bug which was introduced and found in 6.0.2 and is only getting fixed now in 6.0.4. And this bug was hard to understand because in this case, we did not have a reproducible test case. So if we look at the bugs found at each version, we can see that we found about 10 bugs at each version. I don't know if there is much more to say about it, except that we have a steady flow of bugs. What is more interesting is the bugs appearance. So it doesn't depend when we found them. It was when they were introduced in the code. And so we see that most of the bugs were already there before the version 6, almost 2/3 of the bugs. And Fuzzing did not find them straight away. It keeps finding them over time. And I think this is due because we have been improving fuzzing, but also because when we trigger some bug, we get the fuzzer get blocked by it for some time. So otherwise, we see that there were 4 bugs, which in yellow were found and fixed right away in the 7 branch. And about 10 bugs which were introduced after version 6. Most of them were about the HTTP2 traffic analysis, so which was introduced in version 6. Another interesting data is that most of the bugs are triggered by network input, so about 75%, more than 75%, the remaining being triggered by signatures parsing only. So the network triggered bugs look more interesting to us. And about the impacts, there are only a few which could lead to remote code execution. So 6 of them out of the 50 ones. And most of them will are about partial denial of service. If we split this into more detail, we can see that remote code execution is half use after free, half buffer overflow. The complete denial of service is mostly null dereferences, but also a bit of rest panics and I guess 2 buffer overrides. And partial denial of service are mostly evasions that are failed assertions. And then we have timeouts and memory leaks. So this is quite interesting about the evasion, and we have been using more and more assertions to catch bugs because we know that fuzzing is useful for such cases. So that may explain why the green part is so big there. And about the timeouts, I would like to show you this almost perfect graph, except for the middle point data, which shows timeouts found in libhtp, so HTTP1 parsing, which were all due to quadratic complexity. And these were all the latest bugs found, we can say. And we can see that the minimum size to trigger the timeout keeps increasing every 6 months. So now we did not have any new timeouts since March, so maybe we managed to erase all quadratic complexity algorithm in HTTP1 parsing, hopefully, or maybe we will get one another soon. To complete this overview, I would also like to highlight the bugs which got missed by fuzzing. So I did not do that for all the bugs in 6.0. I just did that for version 6.03. So we have 34 redmine tickets with 1 duplicate and 1 irrelevant, leaving us 32 tickets. 10 of them were bugs which were found by OSS-Fuzz, 9 only by OSS-Fuzz, and 1 with double reports from OSS-Fuzz and otherwise. And there were 22 misses. So the question is, why did we miss these bugs? So there is one bug which was not, in fact, in Git master and was in the 6th branch. So we fuzz only master branch, so that's why we missed it, the orange part. The gray part is some missing config option, which is not used by the fuzzer, which in this case is the multi-threaded logging output, which had 2 bugs in it. The yellow part is some parts which are clearly not covered by the fuzzing targets. So one is about setting a config option on the command line, and one another is about using the variables defined in the SuriCata YAML configuration file in some rules in some specific way. Okay, for this small part. Then the most of them, so 12 are were missed because of their kind of semantic. So it's about should we print A or B, and there is no easy solution. There is no ground truth. So at least no ground truth accessible to the fuzzing framework. So these look hard to get. When then the light blue is the interesting part, because I don't really know why the fuzzers missed them, because they look reachable. So there is one case among them where I'm pretty sure that we were missing an element in the base corpus to get there, being about flash file decompression. We had no test case about it, so that's why the fuzzers did not get there, I guess. But there are other, and including one which is which could lead to a remote code execution, which were not found by fuzzer. And so we reached the final part. How did we manage to get that many bugs? What improvements have we've been continuously bringing to Suricata fuzzing? So I guess the most important thing is the coverage. So your fuzzer cannot find bugs in code it does not cover. That is, I guess, the truth. Being about fuzzing or whatever testing framework you use. And Suricata being a mix of Rust and C, we had to done to report for both Rust and C code at the same time. So you have a link to a few pull requests to where we managed to get it. And when we managed to get our first coverage report, I was astonished and disappointed that Rust coverage was low. You see the line coverage is 21%, and I was expecting it to be like 60% or higher, because we have put in Rust all the untrusted input handling. So that's also what we fuzz. So we should cover more. And just having this coverage report, I started digging and found out that the main reason that we were not using all the needed Rust flags compilation for fuzzing. And so right after it, we fixed it, and by the end of the month, you can see that the coverage for Rust had increased to over 70%, which was more what I expected in the first place of fuzzing. And here you can see over the month of March, or the middle of it, this coverage getting increased in terms of lines of code and of percentage of lines covered. There may have been also other code modifications during this period. I did not look into it. But then we studied a bit more the coverage report, and we found that the SMB protocol coverage was still pretty low. And we have a first target, which is about app layer parsing, which should get it covered. And this first target makes a big switch case over the first byte of data, Or if we set an environment variable, we can have one specific protocol such as SMB or HTTP or FTP to be fuzzed. And when I forced SMB protocol and added a fuzzing dictionary with one entry being SMB, I see that the coverage was better in seconds than the one OSS days. So we split the first target. Say we will not do one for every protocol, but one for each of them. And the results are that we found 10 more bugs, or 8 if I add correctly, with this specific first target, when we found 0 with the generic one, since these specific targets were introduced. So this was a successful improvement in terms of bugs found. So structure-aware fuzzing has been helpful for Suricata. So I created a small library, which is fuzzpcap, whose goal is to supply fuzzing-friendly input which describes network traffic. So basically a list of packets, a list of buffers. When libhtp is more complex and is being fuzzed itself, we want to fuzz the core of Suricata, not libhtp. And this library also offers the feature to have network traffic representing a single TCP stream and computing all the sequence and ACK numbers, so that we have a valid TCP single stream and we can fuzz the traffic in it. And in this case, the original target still managed to find one bug, but the new structure-aware target found 10 of them. So that was still a good success to bring this to Suricata. But as I said, this is a continuous effort to improve. One area where there is more work to be done are the performance of the first targets. So we have a proof of concept where we generate a Flamegraph for the run of a fuzzer. And I will show you one sample of this Flamegraph, which has a lot of interesting data. But I would like to highlight just one thing. On the right side, you may see the JSON anomaly logger, which is 70% of the time spent by the first target. And while there may be bugs in the JSON anomaly logger, I do not think it is worth 70% of the CPU power. Because it's not 17% of the code. But fuzzing produces lots of anomalies. So there is a lot of improvements to be done in terms of performance of the first targets. So I'm reaching the end. So to conclude about the improvement summary, there is the coverage and performance report and the continuous investigation, which helps to find potential for optimization. There was the first target splitting, which helped find 10 more bugs, as well as the structure awareness. And then there were also minor changes, which helped find more bugs, like extending configuration to cover the more cases possible, adding more assertions in the code, and also keeping asking when a bug is not found by the fuzzers, why is that so? should we extend the configuration or something like that. And there are more improvements to be done. So while preparing this presentation, I added another target with using the default rule set and fuzzing only as input the network traffic, which found the two latest bugs. So it looks another success so far, but it's quite new. There is always more coverage and performance inspection to be done. There is also one target which I would like to do about differential fuzzing to find evasions when we split the TCP stream differently. And there is one unsolved problems about blockers where we have bugs which we keep private until the next release, and so the fuzzers keep triggering them for 3 months or so until the next release, and then they can explore new code and find new bugs. So there is still more work to be done in that way. In the meantime, I thank you, and we have now some time for questions and answers.